right? Because remember what the order of an element is. It's the smallest positive integer k, such that when you take an element and raise it to that power, to that integer, you get e. Okay? Now, if x is e, this k is 1, right? Because e to the 1 is just e. Okay? So the order of the unit element is 1, and that's true of any group, because every group has to have, by definition, otherwise it's not a group, it has to have a unit. Okay? So here, so you've got a finite group A, and every element, for every x belonging to A, where x is not equal to the unit element, x squared is e. Okay? Where every element other than the identity has order 2. Okay? Has the order 2. The k here is 2. Right? And let this be the minimal generating set. Okay? So you A1, A2, ... AN. That is your minimal generating set. I'll shorten that to just MGS, minimal generating set. Okay, you're given that, all right? For this abelian group. Well, as you know, actually part of the proof is to show that it's abelian, right? So for the moment, it's just a set, a group. Right? It's just a group. All right. So part one of this theorem is to show that it is, to prove that it is abelian. Okay. So show part one. Show A is abelian. And I'll come back to part two once we've proved this, and do step at a time. Okay, so how to prove that this is abelian? All right. Now, so what we have to show is for all A and B belonging to A, AB equals BA. And we know this property is true. All right. Here's the proof. Take AB squared, the square of AB. AB is, I don't know, some element C belonging to this group. So C squared will be E. So whatever this is, square it, it'll just be E. Okay. Now even E squared is still E. So this, the squaring of all elements gives you E, because E squared is E, and all the others as well. But you can't, from that you cannot say that all elements are of order 2, because the E is always the exception. It has order 1. Right? So we've got this. So this is AB, AB. All right. Now here's a trick. Take a look at this and this, and pre-multiply, that means on the left, by A, and post-multiply, this and this, by B, and watch what happens. So we'll get A, E, B from here, right? So we pre-multiply by A and post-multiply by B, and do the same thing here. So we'll get A, B, 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 right? Now, this is just AB, okay? Now, A squared is E, so this is E, BA, and B squared, also E, okay? So this is just BA, and there it is, AB equals BA. So we've proved that this group is abelian, okay? So it makes sense labeling it big A. Alright, now the second part is a lot harder. Have you noticed that these proofs are getting harder as we go? And it's not surprising, because Well, we're well into senior level now and approaching M1. We're almost getting post-grad. Now it's fuzzy, right? It's debatable what's senior level, what's master's level, but the theorems are getting a bit harder. All right, now part two. Part two says that every element of A, every element of this abelian group, we now know it's abelian, we just proved it. Okay. Every element A can be written uniquely, I'll underline that word uniquely because it's highly relevant to the proof, can be written uniquely in the form, so for all x belonging to A, x can be written in the following form. In terms of the MGS, in terms of the minimal generating set of these. So it can be written in the form of eta 1, A2, eta 2. I'll explain what these etas are in a minute. Dot 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 A n eta n. Okay. Now, where each for each of these e's, so I'll just call it I, where I runs from 1 to n. Okay. These take the value 0 or 1. Okay. So I'll say that again. You're given this. We prove, and this property. So all elements are of second order, except of course for the unit, always the exception. And because of that, prove that it's abelian. We're also given for this set a minimal generating set, which has n elements in it. Okay. And the proof is, the theorem states, part 2, that any element x belonging to this group, this abelian group, can be written in this form using the minimal generating set. Okay, so this A1 here is this element, and A2 is this element, and the power here, these etas are integers, and they can only take two values, either 0 or 1. Okay, that's what you have to prove. And so every element of A can be written uniquely. So the way of writing this is unique. There's just one way to do it, right? So how to prove that? No, it's non-trivial. So let's do it in two steps. And actually, this proof method is relatively new to you. You will first make it sound plausible. You'll show in two steps. So first step, we will show that there is a solution of this form. Okay. So that part of the proof, this two-part proof, showing that there is a solution of this form, is the existence proof, right? Showing that a solution exists, that there is at least one solution. Okay, and the second part is, given that there is a solution, you then have to prove that it's unique. Right? I mean, if that's what you're asked to prove, and we're asked to prove that this is unique for a given element. So, and how do you prove uniqueness in general? Well, we've done that sort of thing at least twice before. We've proven that the unit element of a group is unique, right? And how did we do that? By supposing initially there was a second unit, so E and E dashed, and we proved that E dashed actually equaled E. Right? So we'll do the same here. We'll assume that there are two forms like this, that the same element can be written in two ways. So instead of having beta's up here, we'll have something else, right? And we will prove that these two forms are the same. So that shows uniqueness. Alright, and the other thing we proved that for each element there was only one inverse, right? And we did that by proposing there was a second one dashed, and we proved that that was equal to that. Right? So each there's only one inverse in a group for each element. Okay. And all right, so let's start now this two-part proof. A, we have to prove the existence. In other words, there is at least one solution. Okay, and then once we have a solution, we then need to show that that's the only solution, that it's unique. Okay? That in this case, that this element x can be written in only one way, like this. All right, so let's show that there is a solution. Okay. Right. Let's show that there is a solution at least. Okay. So any element in